All right, the next thing we'll begin talking about are discontinuities, what it means to be a discontinuity, what discontinuities look like, and we're going to formalize this idea. If you've been following along in the videos, then when we began talking about continuity, we developed this sort of casual yet intuitive notion or a definition of what it means for a graph to be a continuous graph. So our working definition was a function's graph is continuous if you can trace the graph without lifting up your pencil. So if I give you a arbitrary little graph here, I could start here on the left, trace the full thing with one pencil stroke or one brush stroke without lifting it up and continuing elsewhere. So this right here would be an example of something that is continuous. Whereas if I maybe wanted to change things up a little bit, I could have maybe a function that kind of does this. Now this function here is discontinuous because I could use one brush stroke here, but then I'd be forced to lift up and continue onward. So there's effectively, you can think of it as there being two pieces. So this we would say is a discontinuous. It's discontinuous. We would say, however, that this function is piecewise continuous. So this is a little extra description here. What this means is that as a whole, your function is not continuous, but it has multiple pieces, and each one of those pieces are continuous. So lots of things are piecewise continuous. Okay, so let's get started with talking about these types of discontinuities. We'll get started with the first type of discontinuity that I have listed here. Okay, so this number one would be a removable discontinuity. So this says that the limit exists, but it's not equal to the value of the function. So if I have a limit existing, that means the left-hand limit has to agree with the right-hand limit. And if I were to just actually bridge this little gap here and connect the two pieces, then not only would the limit exist, but the function would also be equal to the limit. And for a jump discontinuity, we specifically, we do not want it to be equal to the value of the limit. So instead what I'll do here is I'll just put a little open circle at x equals, let's say, c. So we know that the limit exists here because we can do a left-hand limit and we get this y value. We can do a right-hand limit and we get that same y value. So we know that the limit as x goes to c of f of x definitely exists, but it doesn't. But for a removable discontinuity, we just need it to not match the value of the function. So this gives us two options here. Option one is that we can just define f of c to be some other value, like up there. Or we don't even have to define f of c at all. We could just leave f of c undefined. So there's an open circle here, but no matter how far up or down you look, you can't find that little dot that would have filled it in. So that's a removable discontinuity. This is also sometimes called a whole discontinuity. So let's also put a whole discontinuity. So another option that we have, let's look at option 2, which is a jump discontinuity. So a jump discontinuity means that both one-sided limits exist, but they are not equal to one another, which is different than what we had the last case here, because the left and right-hand limits did exist and they were equal to one another. So here they can't be equal to one another. So what this effectively means is if the left and right-hand limits exist but they're not equal, that means there is some sort of gap or a jump. There's some sort of measurable distance between the two of them. Now, one thing that this definition doesn't say, it doesn't require f of c. Let's say this is our x equals c. This definition of a jump discontinuity doesn't say that f of c needs to be defined. So again, we have a couple options. We can just leave f of c undefined. That way there's no solid circle here and no solid circle here or anywhere for that matter. There's just open, and there's no circle filled in anywhere else. So f of c is undefined in this case. The other option is that we do choose to define f of c, in which case we can either put f of c here, here, or anywhere, any y value. But this definition of a jump discontinuity, I need to emphasize, it does not say anything about whether or not f of c is actually defined. Jump discontinuities are only concerned with the one-sided limits, that they exist and they are not equal to one another. The last type of discontinuity is an infinite discontinuity. So this definition says that one or both one-sided limits are infinite. They are unbounded. So, for instance here, we could take a look at a really common graph, the graph of y equals 1 over x, or f of x equals x, whatever you want to say. So this graph kind of does this. There is a vertical asymptote here at x equals 0. So in this case, the left-hand limit equals negative infinity. The right-hand limit, as we approach 0, equals positive infinity. So in this case, both of the one-sided limits are infinite or unbounded. So clarification here, infinite doesn't necessarily mean positive infinity or negative infinity. In either case, both positive or negative infinity, they are both unbounded. They are both infinite. So this is not, please do not assume positivity here. Okay, this could be negative infinity. That's fine. So here both, and most functions that you can write down as a single piece, not as a particular piecewise function, if you just write down an arbitrary function, you're going to usually find it where both the left and the right-sided limits are infinite. But if you have a piecewise function or something that you can define a little bit more cleverly, it is possible to have a have only one of the two one-sided limits be infinite. So for instance here, let's just go ahead and let's just say I have a vertical asymptote here at x equals 1. And then I can go ahead and draw my function to maybe do something like this. And then it's undefined there, so I'll put it like maybe I'll put an open circle right here. There we go. So the function so f of c in this case is undefined. And we have the left-hand limit in this case, as we approach 1 of f of x. This would be equal to positive infinity. And then in this case, the right-hand limit, so as x goes to c, as x goes to 1 from the right, this would exist. All right. So a couple other things that we want to talk about really briefly here. Definition 3. What does it mean to be discontinuous? Well, this is sort of a funny definition to me. A function f is discontinuous if it is not continuous. Well, duh. That just seems way too obvious. But a lot of things in mathematics are defined in that way, where if you have something that can either be one of two things, you only bother defining the one option to be the thing, and then you define the opposite of that thing to be, well, the opposite. So this is a very common definition, style or method of defining things in mathematics. You define something, and then you just defined the negation to be quite literally the negation. So, not much to say there. Remark number 3, continuity on a set. This one is really just how we speak in mathematics. So if we have some sort of set I, so some collection of real numbers, and we know that for every value, every number in this set I, if the limit of the function as x approaches that value equals the value of f of c. So again, this right here is our this right here is the definition of continuity. If that's the case, then we just say that f is continuous on I. So what I could say here is, what we could take a look at here as a quick little example is, I could have a function like x squared. So x squared is continuous on all real numbers. Or maybe I have a function where my domain is not all real numbers. Maybe I have got this. This is the natural log of x. It is continuous on the positive numbers, the domain of natural log. You can even have a function that maybe is discontinuous in some places and still be continuous at other locations. So for instance, let's take a look at this graph here, which is, it has value -1, and then it jumps up, and it has value +1. So let's call that f. So this right here, we could say that f is continuous on 0 to infinity and -infinity to 0. We can't include 0 here, but we can say that. We also cannot say that f is continuous on the real number line, because that's not true, because at 0 it's not true. So that does not work.